Chapter 19 is on constrained nonlinear least squares. So this is where we have not only nonlinear least squares, but we also have equality constraints. This time, they're not going to be linear equality constraints as they are in linearly constrained least squares. They're going to be nonlinear equality constraints. Okay, so let's see what the problem is. Well, it's going to look like this. We're supposed to minimize. This is norm. Whoop, there we go. This is norm f of x squared, where f is the vector. And then subject to, we have p equality constraints, but these are equality constraints with possibly non-affine functions gi. And we refer to gi of x equals 0 as the ith scalar equality constraint. So in vector notation, it's just this problem right here. A lot is being hidden there. Here, f is a vector, so that's a sum of squares. G is a vector also, a p vector, and so that's a set of p scalar equations, scalar equality constraints or equations that have to be satisfied. So we say that x is feasible if g of x is 0. And x is a solution, or x hat is a solution if it's feasible, that's required. And if for any other feasible point, it has an objective that is at least as big as our point x hat. Now, in general, this is very difficult to solve if you mean actually literally finding a solution that you know is a solution. But as with nonlinear least squares, there are very good heuristics that solve it quite well, and they solve it well enough to be very useful in practice. Again, it's very much like k-means. It's not like QR, right? The QR factorization, that is not a heuristic. It just works, period. Or, you know, when we solve linearly constrained least squares problems, that is not a heuristic. We simply get the solution, period. Here, we have an algorithm that, you know, might get the solution, might not, which sounds kind of weird, but in fact, if it's useful, that's good. And in many cases, it's very useful. So the Lagrangian of the problem, so what we'll do is we're going to work out the optimality conditions for the constrained nonlinear, constrained nonlinear least squares. And so the Lagrangian is obtained this way. You take the objective, which is going to be norm f of x squared, and what you do is you form, you take so-called Lagrange multipliers. These are numbers z1 through zm, zp. This should be p actually here, so that's a mistake. There you go. Through zp, and what we do is we multiply each of our constraint functions by zi, and we add that up. And so this becomes the Lagrangian, and you can write it in very compact vector and matrix notation, I guess just vector here, this way, as the norm squared of f of x plus g of x transpose z, and z is this vector of Lagrange multipliers. Now, what the method of Lagrange multipliers tells us, this is from calculus, is that if x hat is a solution, then there has to be a set of Lagrange multipliers z hat that satisfies the following. The partial derivative of this Lagrangian with respect to xi is 0, and the partial derivative with respect to zi is 0. And there are some technical conditions which I don't intend to get into, and but I don't even think we have to worry about it. Now, in this case, you would say that when you find an x hat that satisfies this and a z hat is called an optimal Lagrange multiplier. So it actually has an interpretation, but it's not one that we're going to worry about in this course. So that's it. Now, I should mention that there are points that satisfy these conditions, which are not the optimal point. That's the same as nonlinear least squares, so same story. So to work out what these two gradients are, so that's the gradient of L with respect to x and the gradient of L with respect to z, we can work that out. So the gradient with respect to x that's actually the same calculation as in nonlinear least squares, and you get two times, that's the Jacobian or derivative matrix of f at x hat, transpose f of x, plus, and then, so this is what you would see in the case of nonlinear least squares. But here there's an extra term, which is the derivative of g, or the Jacobian of g of x hat transpose z hat. The gradient with respect to z, so that would be How do you take the gradient of the, well, look, it's a pretty simple function in z, right? It just is z, it just simply, it's this one right here. So in fact, the gradient is g directly. So the second set of conditions in the method of Lagrange multipliers tells us that g of x hat is 0. Now, truthfully, we knew that already because this simply says x hat is feasible. It doesn't say anything else. But this is the other condition. And you can actually, it's good to make sure that this generalizes correctly nonlinear least squares. So if there's no constraints, you just remove this and you remove that. And sure enough, we're back to, that's the optimality condition for nonlinear least squares. Okay, now, again, I'll say this condition is necessary for optimality, but it's not, but it's not sufficient. There are points that can satisfy this, but they're not optimal. Okay, let's look at constrained linear least squares as a special case. So here's the problem, looks like that. And then what we do is, this is the same as the nonlinear problem, but we set f to be ax minus b and g of x to be cx minus d. So in that case, f and g are both affine functions. When you apply, I mean, I can tell you what df is. df is a, literally the matrix A, it's constant. dg is c. So when you translate that to our optimality conditions given in the general case right here, here's what you're going to get. It's this thing that's equal to 0, and it's that. And you look at these closely and you realize, like, oh, these are exactly the KKT equations for the linear constrained least squares problem here. And of course, we assemble those typically into a matrix that looks like that matrix equation, and you'll recognize the so-called KKT matrix here on the left. And so in the case of linear least squares problems, you simply solve that set of equations and you have your solution. You also have the optimal Lagrange multiplier z hat. There are applications where you'd want it, but as far as we're concerned, or at least in the scope of this course, we don't have to worry about that. What we're going to do now is look at a simple, very simple method for approximately solving the non-linear constrained least squares problem. And so we'll look at that, and then I should tell you that this is actually the precursor to the method we're actually going to suggest. This is going to be a so-called penalty method, very simple idea. And what we'll do is it's got a drawback, and we're going to come back and fix that drawback with a variation on this method, which is called the augmented Lagrangian method. And that we'll consider in the next section. But for now, we're just going to look at a simple method. So here it is. Actually, instead of a constrained problem, we're going to think of it as what we're going to do is think of the problem as a bicriterion problem, and we're going to think of mu as going to infinity or something like that, right? Because, I mean, if you think about it, if you were able to solve this problem for mu larger and larger and larger, that's going to become a solution of the constrained least squares problem. Because when mu gets really big, you're basically saying that you have no choice but to make g of x equal to 0, and that's what we want. So now this is itself a constrained least squares problem, like that. So it's just that, depending on the value of mu. And we could use Levenberg-Marquardt to minimize that. And so that looks like this. I take an increasing sequence of the mu's, like mu1 equals 1, then 2, then 4, 8, 16, that's something, doesn't matter. And what I'll do is I'll compute xk plus 1 by minimizing this using Levenberg-Marquardt. But here's an important part. I'm actually going to start at the previous point. That's important, actually. That's called warm start, by the way, instead of cold start. Cold start starts with x equals 0 or x equals some random vector. But we're going to start with the previous one. And we'll see how that actually lends us an advantage soon. Okay, so let's take a look at this and see how this method works. By the way, this method works okay. It's just not so bad. I mean, one minor problem is that you might get really big, and you might have some big gradients and things like that flying around, but it actually kind of works. We'll see another method that doesn't suffer from that, but for now we'll look at this one. Okay. So remember that for the constrained nonlinear least squares problem, the termination condition, the optimality condition is this. Okay. Now let's suppose that what we do is instead of solving the original problem, we solve this one, but for a given mu k. Okay, well, if I do that, I just write down the optimality conditions for these optimality conditions for this nonlinear least squares problem, and that's going to turn out to be exactly this. That is the optimality condition. Okay, now what we're curious about is how does this relate to that? We have intuition that tells us that when mu k gets really big, this gets closer to a solution of that. But if we stare at it long enough, you realize, hey, look at this. If we take the following, if I put this 2 mu k together with the gxk, we see that this is dg of xk transpose and then times this thing times that. That's a scalar, so it can move inside. So I'm simply going to define zk to be this thing, right? And in that case, we'll say that this algorithm produces a sequence xk and zk, and this holds. And that's really kind of cool, right? It says that we produce, remember that you have two conditions to determine optimality condition for the original problem, right? It's this one, right? Some people call that the dual condition. They have lots of names. And this is called the primal condition, or it simply says that the point is feasible, right? So this says that first one we get for free. It's just completely free. We get a z, well, with this zk, it comes for free. And so the only thing we really have to worry about then in this algorithm is that one is becoming feasible. So people would say that with this penalty method, quote, it converges to feasibility. So as the algorithm runs, you get closer and closer to having a feasible point. By the way, when you have a feasible point, you have a point that satisfies the optimality conditions. Okay, so that's the idea. And so you stop the penalty method when the norm of g of x is sufficiently small. Now, of course, that alone just tells you you found an almost feasible point. But this thing, because of the way we've constructed it, this guarantees that, in fact, the other condition holds, which is kind of cool for an appropriate choice of z. Okay. Let's look at an example. It's completely made up, but here it is. It's f of x1 and x2, two variables, is going to be, x1 plus e to the minus x2, and then some quadratic, x1 squared plus 2x2 plus 1, right? And here's g of x. It's just one. It's one equation. So p is equal to 1. And it basically says, minimize the norm squared of this expression subject to this equation equaling 0. Now that's going to trace out a curve in the plane, in the x1, x2 plane. Let's take a look at that. Here's x1 and here's x2. This dashed curve right here is the feasible set, right? That's the point where this equation, this is equal to, that thing is equal to 0, and that equation holds, okay? These level curves here, right? These tell you the level, they're the level sets of norm f of x squared, right? And so what we really want to do, these are large values up here. These are getting smaller and smaller. And so along this line, this curve, which is feasible, we want to find the point that has the smallest value here. And that's actually right here. That's x hat. That's going to be your smallest value. So that's the picture of what this looks like. Okay, so let's see how our penalty method works on this problem. We'll take mu1 equals 1. And what we'll do is we'll find x2 right here. Then when we say mu2 equals 2, what you're going to get, so here these the curves, the solid curves are the contour lines of actually the objective plus mu k times g of x squared, right? So we're approximately minimizing it. This dashed line here shows you the feasible points. And in fact, all we need is for the point we're calculating to be on that feasible set. That tells us that we're feasible. So at least we can do this at least visually with some of these things. So, okay, so here we get this point. Then on the next step, you can see actually that these curves have changed because mu k has gone up, and with the point we compute is closer. Here, by the time it's 4, you're closer still. And if you fast forward up to mu on the 6th step, mu is 32. you can see that you're pretty close, that you're getting pretty close here, and it's actually it appears to be converging to the solution. It is actually. So the convergence for this looks something like this. Here's the number of oh, and I should say what the iterations are. The unit of effort is actually carrying out a Levenberg-Marquardt iteration. That means calculating the derivative of d and of g, number one, and number two, actually solving a least squares problem. So there might be like, 15 Levenberg-Marquardt iterations for one outer iteration in the penalty method. And so we actually keep track of the number of Levenberg-Marquardt iterations. And we're plotting two things here. The feasibility, and that's the feasibility here, and and then the so-called optimality one. So the blue curve shows you the norm of g of x, and when that goes to zero, that means you're feasible, right? So you can see down here, 10 to the minus 4 is, we're going to call that close enough. The red curve shows the norm of this thing, and so that becomes zero basically after the first Levenberg-Marquardt cycle is here, and it stays small. And you can see that's kind of the point. And then when both are less than, I suppose my condition here for terminating is 10 to the minus 4, but when both get to be less than 10 to the minus 4, we quit and we declare success. Okay? Here's the value of that penalty parameter, right? The first Levenberg-Marquardt cycle takes 50 some odd iterations, okay? And that lands you here. Then you're 1. Then it jumps up to 2, then 4, then so on. And that shows you how this works. And one thing you might be concerned about is by the end here, our mu is 10 to the 4. Well, maybe you're not concerned about that, but that's how that works. Is that parameter gets bigger and bigger and bigger, and it kind of makes sense. So that's the idea behind this so-called penalty method.